Okay, hello and welcome back. And uh, where we left off last time was we were talking about oxidation states. And oxidation states in oxidation reduction reactions are sort of hypothetical charges that we place on atoms for the purpose of keeping track of electrons, where they are and where they're going to, so we can keep track of what's being oxidized and what's being reduced. Because remember the memory device Leo says GER, that is, loss of electrons is oxidation, gain of electrons is reduction. So every redox reaction includes something losing electrons and something gaining electrons. Electrons are negatively charged, so when something loses electrons, it's kind of like subtracting a negative in math. The oxidation state actually goes up when you lose electrons. And when you're adding negative charges, that means your oxidation state goes down. And to assign oxidation states, we basically just assume that each atom in a compound is an ion, even if it really isn't, because that allows us to keep track of where the electrons are going in a bookkeeping type of situation. But it's important to remember, unless the substance involved really is an ion, oxidation states are hypothetical. They're not real charges. The real charges on the atoms in something like H2O, for instance, are partial charges. And they're hard to, that you can calculate them, but they're hard to calculate, and it's way more trouble than we really need to go to. And so we look at the hydrogen and the oxygen as if they were ions. And so for oxidation states, we would say, okay, hydrogen, if it's an ion in combination with another nonmetal like oxygen, hydrogen would have a charge of +1. And so we give the hydrogen in H2O a charge of +1. And the same is true for the other hydrogen. Oxygen, on the other hand, if it's an ion, its normal charge as an ion would be -2. So that's what we write for the oxidation state of oxygen in H2O. And we can use those numbers again to keep track of whether oxygen or hydrogen in the H2O molecule are gaining or losing electrons during a reaction, just by finding out the oxidation states of those elements in whatever compounds they go to during the reaction. Remember, the total of oxidation states for a molecule with no overall charge like water has to be 0. And notice that +1 +1 -2 does indeed add up to 0. If you're dealing with a polyatomic ion, like NO3-, the nitrate ion, then the total of all of the oxidation states of all of the atoms in the formula would have to add up to the charge on the ion, which in the case of the nitrate ion would be -1. We went over assigning oxidation states at the end of the last lecture, and I'm not going to go over that again because it gets a little tedious and involved, so I'll just leave that where it was. And these rules for assigning oxidation states are all in the book. But what I wanted to introduce was a method for assigning oxidation states when dealing with nonmetals, that is, covalently bonded compounds, which would be made up entirely of nonmetals, compounds like H2O or CO2 or things like that. There is an easier method for assigning oxidation states, and I'm really not sure why the book didn't mention it at this point. I'm sure they'll mention the concept later, but this seems like it would have been a good place to introduce it. And that is the concept of electronegativity. Electronegativity is the attraction of an element for electrons within a bond. And so in the H2O molecule, the fact that the oxygen has a negative charge on it indicates that the oxygen has a greater electronegativity, that is, a greater attraction for electrons, than the hydrogens do. And so the electrons in the bond between the oxygen and hydrogen are being pulled closer to the oxygen because the oxygen has greater electronegativity or greater attraction for electrons within that bond. And they're being pulled further away from the hydrogen. But they're not being taken away from the hydrogen completely. So that's why we say the +1 and -2 charges are hypothetical. The real charges would be maybe plus 0.3 for the hydrogen and negative 0.6 or something like that for the oxygen. But we don't need to know the exact charges. We can just use these hypothetical charges just to keep track of where the electrons are. Anyway, the electronegativity is the attraction, again, of an element for electrons within a bond. Different elements have different levels of attraction for electrons within a bond, as we just saw with H2O. You can actually assign a number to each element for its electronegativity. And in fact, if I don't know if anybody has ever heard of Linus Pauling, he was probably one of the most famous chemists who ever lived. And he won a Nobel Prize for coming up with the idea and the numbers for electronegativity. He's also one of the few people who's ever won 2 Nobel Prizes, one for chemistry and actually one for peace because of his anti-war activities later in life. So he's probably actually better known for that than he was for being a chemist. But anyway, if you look at the periodic table, there are trends going up and down and back and forth across the table, and a lot of different properties associated with the elements. And electronegativity is one of those trends that varies in a predictable way within the periodic table. The trend of electronegativity in the periodic table is that it increases, and I've drawn it over there, but it's kind of hard to see, going from bottom to top and from left to right. And that's except for group 8A. Group 8A, of course, being the noble gases, they are very happy the way they are. They don't want to gain any electrons and they don't want to lose any either. So they would have very low electronegativities. The lowest electronegativities for all of the elements would be cesium and francium, which are both down in the lower left-hand corner of the periodic table. And the highest of all would be fluorine, which is up in the upper right-hand corner of the table. So if you look at an actual periodic table, you see cesium and francium are down here in the corner. Those have the lowest electronegativities of any elements around. They will practically throw electrons at you just for looking at them. And on the other hand, you have fluorine up in the upper right-hand corner, which has a voracious appetite for electrons. Fluorine will actually take electrons away from glass. You cannot store fluorine in anything made of glass because it will eat right through it by taking electrons away from the glass. And the trend basically goes up as you're going up the table and up this way also. And you can kind of see it because the two extremes are in the opposite corners. And of course, these guys are the noble gases and they don't fall into the trend. And the rule for assigning oxidation states in covalently bonded compounds, that is compounds that involve nothing but nonmetals, is actually pretty simple. The most electronegative element has the oxidation state that it would normally have if it were an ion. And everything else just takes whatever charge it has to in order to make the overall charge work out. And I've got it written again on the next page because I kind of ran out of space there. So the rule is the most electronegative element present has an oxidation state that is equal to what you could call the favorite charge on its ions. And the favorite charge of an ion for a nonmetal is group number, that is group number using the AB system, -8. So for instance, for fluorine, fluorine is in group 7A, and so its favorite charge as an ion would be 7 - 8, which is -1. Okay, but that only goes for the most electronegative element in a compound. The other elements take whatever charges they need to in order for the overall charge to work out. And again, if it's a molecule, then by definition, the overall charge would be 0. If it's a polyatomic ion, then the overall charge would be whatever the charge on the polyatomic ion is. And I've done some examples here working out the charges using the electronegativity method. They go over some examples using the book method in the book, so I'll leave you to look at that. But you should be able to use either method and end up with the same oxidation states. If you have something like sulfur dioxide, This is a compound. And so if we refer to something to a formula as a compound or a molecule, that would mean that the overall charge is 0. And so I usually put parentheses around it and write a little 0 as a superscript after it, just to sort of remind me that all of the oxidation states within the formula are supposed to add up to 0. Out of the two elements here, sulfur versus oxygen, well, according to the trend, oxygen should be the more electronegative of the two. And sure enough, oxygen is above sulfur. And remember, the trend is that electronegativity is increased going up a column. So sulfur should be less electronegative than oxygen. And it is. Oxygen is actually second only to fluorine in terms of electronegativity out of all of the elements. Goes first is fluorine, second is oxygen, and then chlorine. So oxygen gets to take its favorite charge as an ion. Oxygen is in group 6A, so its favorite charge as an ion would be 6 minus 8, which is minus 2. Okay, so the oxygen is minus 2. And then you have to work out what the sulfur is. Sulfur, let's see, if each oxygen is minus 2, and there are 2 of them, then that's minus 4 for the oxygens collectively. And there's only 1 sulfur to bring that minus 4 back up to 0. So the sulfur must be plus 4. And that's what it is. Sulfur is plus 4. Now notice that sulfur is in the same group in the periodic table as oxygen. And so sulfur's favorite charge as an ion would also be minus 2. But you can't have sulfur being minus 2 in that compound, because if sulfur is minus 2 and oxygen is minus 2, you're going to end up with an overall charge of minus 6, not 0. So if these charges are going to total up to 0, then again, the most electronegative element can take its favorite charge, but that leaves the other element to be whatever it has to be in order to make the total 0 in this case. So sulfur doesn't get to take its favorite charge as an ion. It has to be plus 4 in this case. There's also a compound, sulfur trioxide, which is SO3. It's also a compound, so the overall charge is 0. And it has the formula SO3. Since it's sulfur and oxygen again, that means oxygen would still be the most electronegative element present. And so oxygen gets to have a charge of minus 2, like it would normally want to be. And that leaves sulfur to be something else this time. So we're going to have to figure that out. If each oxygen is minus 2, and there are 3 of them, that would mean minus 6 for the oxygens collectively. And there's 1 sulfur to bring that back up to 0. So the sulfur here must be plus 6. And that's what it is. You also have the sulfate ion. The sulfate ion has the formula SO4 minus 2. And so all of the oxidation states in this case are going to have to add up to minus 2. Again, though, with the elements, it's a choice between sulfur and oxygen. Obviously, again, oxygen is the more electronegative of the two. So oxygen gets to take its favorite charge as an ion, which is minus 2 again. And if each oxygen is minus 2, and there are 4 of them, that would mean that there's a charge of minus 8 collectively for the oxygens. And again, there's only 1 sulfur to bring that up to minus 2 this time. You're not bringing it up to 0, you're bringing it up to minus 2. So to go from minus 8 to minus 2, that's a difference of 6. So sulfur here is also plus 6, just like it is in SO3, the molecule. Okay. We can look at the example of ammonia, which is a compound. So it has an overall charge of 0, and it has the formula NH3. This is kind of an exception to the way we normally write the formulas for compounds. We normally write, when we're writing the formulas for the compounds, we usually put the less electronegative element first. And also, now that I think of it, actually what we said at the time was we put the most metallic element first and the less metallic element second. Well, the most metallic elements are the ones down here in the lower left-hand corner. And the least metallic elements are the ones up here in the upper right-hand corner, not counting group 8. And so that what that means basically is the higher the electronegativity, the less metallic an element is, and the lower the electronegativity, the more metallic the element is. So saying that we normally put the less, or so that we normally put the more metallic element first is just another way of saying we normally put the less electronegative element first. And when it's a choice between hydrogen and nitrogen, in terms of electronegativity, hydrogen would actually be more like over here. But anyway, clearly from this, hydrogen is less electronegative than nitrogen. So by all rights, the formula for NH3 really should be written as H3N. But ammonia was so common and so well known by this formula that they decided to just leave it alone and let it be. So it's written NH3. Out of those two elements, again, nitrogen is much more electronegative than hydrogen. And so the nitrogen gets to take its favorite charge, the charge it would have if it were an ion. And the nitrogen ion is known as the nitride ion, and its charge, because nitrogen is in group 5A, its charge would be 5 minus 8, which is minus 3. Okay, and that's because basically it needs to gain 3 electrons to get to the same number of electrons as the next coming noble gas. 1, 2, 3. So N has a charge of minus 3 on it, and that leaves hydrogen to be, well, whatever it has to be in order to make the overall charge work out. Now, we've said in the past that hydrogen is always +1 when it's with other nonmetals, and it's always -1 when it's with metals. So we're kind of hoping that it works out that way. And sure enough, it does, because if nitrogen has a charge of -3, and the hydrogens have to bring that charge up to 0, so the hydrogens collectively have to have a charge of +3, but there are 3 of them, and there's no reason to think that they don't share that charge equally, so that would be +1 each. And so hydrogen is indeed +1. There are numerous compounds between nitrogen and oxygen. One of them is N2O4. I chose that just because neither of the subscripts is 1, so we haven't seen an example like that yet, with no 1s as subscripts. So this is a compound. It's Dinitrogen Tetroxide, which literally just means 2 nitrogens and 4 oxygens. And it's a compound, so the overall charge is 0. And out of these two, nitrogen and oxygen, nitrogen is pretty electronegative, but oxygen is the second most electronegative element of all, second only to fluorine. So oxygen is definitely more electronegative here. So oxygen gets to take its normal charge as an ion, which is -2. And nitrogen takes whatever it has to make the overall charge 0. So if we're looking at the oxygens, if each of the oxygens is -2, and there are 4 of them, that means -8 for the oxygens collectively. And that means the 2 nitrogens have to bring it up to 0, so that would mean the 2 nitrogens together must be +8. But there are 2 nitrogens, so that would leave them to be +4 each, because that's just 8 divided by 2. So nitrogen is +4. Okay. And let's see, for phosphorus trichloride, again, phosphorus trichloride is a compound, so the overall charge is 0. Between phosphorus and chlorine, you notice phosphorus is here, chlorine is here. Chlorine is to the right of phosphorus. Chlorine is definitely more electronegative. As I said, chlorine is the third most electronegative element of all. Fluorine first, oxygen second, chlorine third. So phosphorus definitely the less electronegative element here. Okay, so chlorine's going to take its normal charge as an ion. Since chlorine is in group 7, its normal charge as an ion would be 7 minus 8 or minus 1. And that leaves the phosphorus to be whatever it needs to be to make the overall charge work out. If each chlorine is minus 1 and there are 3 of them, that would mean the chlorines collectively are minus 3. And that lone phosphorus would have to be plus 3 to bring the charge back up to 0. So phosphorus is plus 3. The next one is an interesting example because it's oxygen difluoride. Here you have the 2 most electronegative elements of all in a compound together. And in every example so far where oxygen has appeared, oxygen has always been the most electronegative element present. But that's not the case here. Fluorine is the big guy. Fluorine is the most electronegative element of all. So here, fluorine gets to take the charge it would normally have as an ion, which is minus 1, since it's in group 7 right above chlorine. And that leaves the oxygen to fend for itself and be whatever it needs to be. So if each fluorine is -1, and there are 2 of them, that would mean the fluorines collectively are minus 2. And there's 1 oxygen to bring that back up to 0. So oxygen must be plus 2. And that's really unusual to see oxygen with a positive charge, but it can happen if it's with fluorine. So oxygen is plus 2. Xenon hexafluoride is one of only a couple of compounds known to form among the noble gases. And notice how you have to combine it with the most electronegative element there is in order to get xenon to form a compound. And XeF6 is xenon hexafluoride. It's a compound, so the overall charge is 0. It involves xenon, which actually has a very low electronegativity, and it involves fluorine, which has a very high electronegativity. So fluorine here is definitely the most electronegative element present. So fluorine gets to take a -1 charge, and there are 6 of them, so that's -6 collectively for the fluorines, and that leaves 1 xenon to bring the charge back up to 0. So the xenon must be plus 6. And then there are some examples over here that I haven't done yet, so I thought we'd work them out kind of together. You can try doing these, actually. Now would be a good time to shut off the video and try and work these out, and then start it up again, and we'll compare results, and we'll go through it step by step, and you can see if you got them right. Okay, so for the perchlorate ion, that's ClO4 with a total overall charge of -1. We know that the total of all of the oxidation states of all of the atoms within the formula must add up to -1. And also, it's an ion formed between chlorine, and oxygen. Oxygen is the second most electronegative element of all, and chlorine is the third most electronegative of all. And so clearly here, oxygen is more electronegative. So oxygen takes the charge it would normally take as an ion. Oxygen is in group 6A, so the charge it would normally take as an ion would be 6 minus 8 or -2. And chlorine, well, let's see, if each oxygen is -2, and there are 4 of them, that's -8 for the oxygens collectively. And that 1 chlorine has to bring the charge back up to -1. So from -8 to -1, that's +7. So chlorine is actually +7 in the perchlorate ion. Now, we've got a whole series of chlorine-oxygen ions. So we have the chlorate ion also, that's ClO3, also with a -1 charge overall. Since it involves chlorine and oxygen again, it's safe to say that oxygen will again be the more electronegative element present, and it will be -2 in charge, like it normally would like to be. Because again, oxygen will always be -2 with any other element except fluorine, like this example right here. So let's see, if each oxygen is -2, and there are 3 of them, that would be -6 for the 3 oxygens, and chlorine has to bring that up to -1. So chlorine must be +5. Sorry. We also have the chlorite ion, which is ClO2 with a -1 charge overall. So again, oxygen is going to be -2 each, but there are 2 of them. So that's -4 for the oxygens collectively, and that 1 chlorine has to bring it up to -1. So the chlorine must be +3. So we're seeing here a lot of the non-metallic elements, like chlorine, for example, can take a whole range of different oxidation states depending on what it's bonded with and what the overall charge is. And we're not done yet, because there's also the hypochlorite ion, ClO minus, sometimes written OCl, but ClO sort of keeps the trend going with the other chloride ions. Again, oxygen is going to be -2, and there's only 1 of them. And so that the oxygen has a charge of -2. There's 1 chlorine to bring that up to -1. So the chlorine must be +1. And we hadn't done very many ions, so here are a couple ions. The phosphate ion has a charge, overall charge of -3. It's between oxygen and phosphorus. And again, oxygen is here, phosphorus is here, and so oxygen is definitely more electronegative. Like I said, it's second only to fluorine anyway. So oxygen is definitely more electronegative than phosphorus. Oxygen will be -2, like it is with everything except fluorine. And phosphorus will be whatever it has to be. So let's see, if it's -2 for each of the oxygens, and there are 4 of them, that's -8. And there's 1 phosphorus to bring the charge from -8 up to -3. -8 to -3 is a difference of +5. So fluorine has to be +5. I mean, phosphorus has to be +5. In the permanganate ion, MnO4 minus has an overall charge of -1. It involves manganese and oxygen. Manganese is actually a transition metal, so you'd expect it to have a positive charge in anything, really. And fortunately, that's the way it will turn out here. And if you're comparing oxygen to a metal, there's absolutely no doubt which one has higher electronegativity, and that will be the oxygen. And so oxygens with metals are always -2. It's oxygens with nonmetals. Actually, it's only oxygen with fluorine where it might not be -2. If the oxygens are -2 each, and there are 4 of them, that's -8 for the oxygens. And there's 1 manganese to bring that back up to -1. So from -8 to -1, that's a difference of +7. So manganese in the permanganate ion is +7. Okay, I decided to do that one because there's going to be an example in a little while involving the permanganate ion, so I thought I'd sort of introduce it here. Okay, so that's how you can assign oxidation states using the concept of electronegativity. I'm a little bit over on the time limit for this segment of the lecture, so I'm going to stop here, and we'll go on with redox reactions a little bit more in part B.